Welcome back. Time for Chapter 8, Equilibrium and Elasticity. So Chapter 8 is kind of a hodgepodge of lots of different ideas. And so we're going to go through and talk about each of them. And it's a nice kind of review of everything we've learned with rotational motion and torque and spring potential energy and spring constants. There's a lot that's kind of in here. Okay, so equilibrium. We have equilibrium when both the sum of forces is equal to 0 and the sum of torques is equal to 0. That means there's no net force and there's also no net rotation, because if there was a net torque, the sum of torques was not equal to 0, then the object would be spinning. So here's an example. In all of these cases, the sum of the forces is equal to 0. So even on both sides, even on both sides, even on both sides. However, in the first two cases, the net torque is equal to 0 because they act on that center point. In the last case, the net torque is not equal to 0 because one acts on the upper side and one acts on the lower side. So it would end up spinning in a clockwise direction. Counterclockwise? Clockwise. Down is clockwise. That's right. Okay. So let's do a little example. Finding the force from the biceps tendon. In the joints of the human body, muscles usually attach quite near the joint. This means that muscle and tendon forces are much larger than applied forces. In weightlifting, where the applied forces are large, holding the body in static equilibrium requires muscle forces that are quite large indeed. In the strict curl event, a standing athlete lifts a barbell by moving only his forearms, which pivot at the elbow. The record weight is over 200 pounds, about 900 newtons. Figure 8.2 shows the arm bones and the main lifting muscle when the forearm is horizontal. The distance from the tendon to the elbow joint is 4 centimeters, and from the barbell to the elbow is 35. And what are we being asked for here? I didn't include that part. It's asking for the force on the tendon. So I should have included the image and the actual question. Sorry about that, but we'll draw it out. Let's see. So here is a diagram. On the outside edge, I have a force down of 900 newtons. And then right here, pushing up, I have the force of the tendon, which is like a tension force, but I'm going to call it the force of the tendon going up, and that's what I'm trying to solve for. I also know that this distance right there is 4 centimeters, 0.04 meters, and the total distance from here out to here is 35 centimeters, 0.35 meters. Okay, so I know that in this case I have 2 torques because there's a pivot point right there. And so I need to set the other way, the torque equal to the torque, and that's force times distance equals force times distance, or diameter, radius, right? So I could use R for radius instead if that works better. Either way, it would be 0, let's see, those would be the force of the tendon, so F sub T, times 0.04 meters equals the force of the barbell, which is 900 newtons, times 0.35 meters. Okay, so now I multiply 900 by 0.35, and then divide that by 0.004, just 0.04, excuse me. And I get 7875, or about 7,900 newtons is equal to the force of the tendon. Cool. Oh, but you know what I did? I made a mistake because I have 2 arms. So this would be the force if there was just one arm lifting, but I split that force between my 2 arms. So what I should have done at the beginning was I should have done my 900 newtons divided by 2 because I'm splitting it between both arms, but I can just do it now. 7,900 divided by 2 gives me 3,900 newtons because of the rounding. So that should be 3,900 newtons on each tendon, right? I'm split between 2 tendons for each of my 2 arms. Good. All right, let's stop and think. Which of these objects is in static equilibrium? Okay, so static equilibrium means that the forces and the torques have to be equal and opposite. So B has more force going to the right. So they're both equal, but they add up to more than that guy. So that one's out because the forces are not balanced. This one, these 2 forces seem balanced, but then they've got an additional force there. So A does not have forces balanced either. C does have the forces balanced, but he's got 2 there, 1 there, and 1 there. And I would need this arrow to be up here, like there, in order to keep it balanced. This one would have some torque, and the torque would be in that direction. It would spin that way just a little bit. Actually, yeah, it would spin that way because this one would be pushing that way just a little bit. So it would have a little bit of torque there. And D has, let's see, there's my center point. I've got 1, 2, and those add up to the total of this guy. So D is in static equilibrium. They're evenly balanced around that center point. And so there's no torque and no net force. Okay, so when we're doing these kind of problems, a pivot point. So we should choose a pivot point to make calculations simpler. Now, sometimes there's a really obvious pivot point, like if this says it can rotate around this point only, like your elbow, the pivot point is really clearly your elbow, right? That's where your arm rotates around. Other times you can make some choices and you can set your pivot point where you want it to keep things in static equilibrium. All right, so finding the center of gravity of a human lying on a board. A woman weighing 600 newtons lies on a 2.5 meter long, 60 newton reaction board with her feet over the pivot. The scale on the right reads 250 newtons. What's the distance from the woman's feet to her center of gravity? Okay, so I've got a system here. I'm going to draw this out again. There's my pivot point. I've got this board out here, and it's called a reaction board. And it says that it is 60 newtons, and that would be right at the center point, right? So that would be 60 newtons down there, and it's 2.5 meters long. So that means that distance for 60 newtons would be at 1.25 meters, because that's halfway through. Then for the 2.5 meters, let's see, that entire thing is 2.5 meters. And there's a scale on here. And that scale's holding it up here. So that indicates that there are 250 Newton force there. So that scale is being pulled upwards, right? The scale is holding it up. And now I need to figure out what's the distance from the woman's feet to her center of gravity. So that's, and her feet are touching the board. So I know that she is somewhere in here, right? Pushing down. I know that she's pushing down at 600 newtons. Okay. And I need to know what's her distance for the center of gravity. Okay. So I can set these equal, right? So remember, I can do this torque equals torque thing. Torque equals torque, right? Set the 2 sides of torque equal to each other. Going up, I just have the 1 set. So that would be 2.5, sorry. I should note that this would be force times the radius, or force times distance equals force times distance. Going up, I have 2.5 meters times 250 newtons, all right? That's the torque that the scale is exerting, equals, I have two sets on this one, right? I've got the weight of the board itself, and that one is going to be 60 newtons times the distance of 1.25 meters plus what I'm solving for, which is her distance, which would be 600 newtons times d. All right, so I'm going to subtract out the 60 times 1.25. So 2.5 times 250 gives me 625 minus 60 times 1.25 gives me a total of 550. So over here, I've got 550 newtons times meters equals 600 newtons times d. Divide both sides by 600. And I get 92 centimeters equals d. It's 0.92 meters or 92 centimeters. So that looks like a valid answer. Almost 3 feet. Yep, that would put you right at kind of your upper hip for a normal sized person. So that seems pretty reasonable. If she's like 5 feet tall, 5.5 feet tall, that would be a valid center of gravity. Okay. Stop and think 8.2. A beam with a pivot on its left end is suspended from a rope. In which direction is the force of the pivot on the beam? Okay, so I have here, the rope is pulling up there. The beam itself is pulling down here. Well, one way of thinking about this is if I just take out the pivot, right? If I get rid of this, which way is this sucker going to swing? It's going to swing down this way. So which way is the pivot holding it? The pivot is holding it up, right? The pivot is exerting a force upwards because if it wasn't there, it would rotate the other direction. So I know it must be going straight up because this point would start by going straight down and then it would swing at the angle, right, as it went further and further. So that would be B. All right. Toppling. So they also throw in some toppling here in chapter 8, which is fun. So an object will topple anytime its center of gravity is outside of its base. So here's an example for a car. The center of gravity is represented by this little circle, right? And right now, the center of gravity is where the weight is, and it is inside the base. It's inside the tire set. So the car is very stable. Let's say the car starts to tilt a little bit. Well, the car tilts and its center of gravity is still inside of its base. It tilts even more. It tilts up to what's almost like a 45-degree angle, it looks like. Still, the center of gravity is right over the edge of the base. So that's called the critical angle. The critical angle is where, right there, the height versus half of the base. Sorry, that's the like the X and Y components there. And then it'll topple when the center of gravity is outside of the base. So now the car will fall all the way over. In these previous tests, the car will fall back onto its base. All right. So let's rank in order from least stable to most stable these 3 objects. Positions of center of gravity are marked. For center of gravity to be positioned like this, the objects must have non-uniform composition. Okay, so for each one, I'm trying to figure out how much would I have to tilt it in order to get it to fall over. So the easy way of doing that is to draw the triangle, right? There's the base, there's the line, and so I can compare their critical angles. That is the critical angle right there. In this case, there is the critical angle. Halfway. And in this case, the critical angle is that guy. So this is the most obtuse angle. It's not actually obtuse, but it's the largest angle. So C is going to be the most stable because its center of gravity is so low. it would have to tip a long way. So I'm going to say C is the most stable, or least stable to most stable. So the least stable looks like B. I think that is the tightest angle based on my drawings, because its center of gravity is pretty darn close to the same height. It's slightly lower, but the base is much, much smaller. Like this has a pretty big base there, so that's protecting it. So I'm going to say B is the least stable, and that's less stable than A, which is less stable than C. Right? C has the greatest critical angle. All right. So let's go back and think a little bit more about springs and Hooke's law. Now, we've introduced this when we talked about energy. We did spring potential energy. And now we're going to come back and just kind of reinforce springs and Hooke's law. So the force of a spring is directly proportional to x, the distance moved by the spring. We can put that into an equation and say that the force of the spring is equal to the negative spring constant k times the change of distance of the spring x, or F equals kx. K is a spring constant, and it's something that is constant about every type of spring. So if you have like a really light spring, like a light rubber band, that would have a pretty low spring constant. It doesn't take very much force to stretch it a long way. If you had a really big beefy spring, like the spring that would hold up your monster truck, for example, like your shocks on the monster truck, that would have a large spring constant because it takes a lot of force to push that sucker down. Actually, I don't know if monster trucks, your regular car might have higher spring constants, because I think monster trucks are designed to like land and compress, like vroom. So maybe they're a little bit bouncier. Whereas your car is not designed to go over other cars and crush them. So your car might have a stronger spring constant. Not sure. In any case, shocks on cars would have high spring constants because it's a spring that is not easy to move. It would require a lot of weight to make it move much. Okay. So this is shown here, the restoring force for a spring. It starts at an equilibrium length. So that equilibrium length is how long it is under normal conditions. I can then squeeze it down a change of x, and then it'll, with a certain force, or I could pull it out a change of x. It could go in either direction away from equilibrium, in or out, in order to, and the same force would be exerted to do both. Okay. Now, the further I pull that spring back, the harder it is to pull. So here I'm just pulling it a little bit, and you'll notice the force is not super long. When I pull it longer, the force required is much bigger, right? Larger force to get a greater change of x. Makes sense. All right, those are a linear relationship because the spring constant is, wait for it, constant for every spring, assuming you don't break the spring, right? If you stretch it out and then it's a broken spring, then you've changed the spring constant. The end of a spring is pulled to the right by 4 centimeters. The restoring force is 8 newtons to the left. Given the relationships shown, if the spring is returned to equilibrium and then pushed excuse me, to the left by 2 centimeters, the restoring force is, okay, so I've moved half the distance. It was 4 centimeters before, and now it's 2 centimeters. So that means it's going to take half the force. It was 8 newtons. Let's see, when I went to the right, it was 8 newtons to the left. Now I'm going to the left by 2, so it's going to be to the right at 4. And that is B, 4 to the right. Okay, so I did half as much, because half of 8 is 4, half of 4 is 2, 4 centimeters to 2 centimeters, so 8 newtons to 4 newtons. And then the direction is going to be opposite because the direction I've gone is opposite. All right. When does the block slip? Figure 816 shows a spring attached to a 2-kilogram block. The other end of the spring is pulled by a motorized toy train that moves forward at 5 centimeters per second. Spring constant is 50 newtons per meter, and the coefficient of static friction between the block and the surface is 0.6. The spring is at its equilibrium length when at t equals 0, when the train starts to move. When does the block slip? Ooh, this is fun. Okay, so first I need to figure out what force is necessary to cause the block to slip. And that's the force of friction. So I can think back and remember that the force of friction for kinetic friction is the coefficient of friction, static friction in this case, because it's sitting still, times the normal force. Okay? And the normal force is equal to the mass times the acceleration due to gravity, or the weight, right? Because normal up equals weight down on a flat surface, and this is a flat surface. So that is going to be mu sub s times mg, which is equal to 0.6 times the mass, 2 kilograms, times 9.8 meters per second squared. We'll multiply all those together. 2 times 9.8 times 0.6, 11.6 or 0.76. Okay. And I'm going to leave it in a lot of decimals for right now. So that's how much force I have to exert in order to get it to slip. Now, I have it on a spring, right? And I also know that so I've got the force of friction is back this way. And then the force of the spring is going to be that way. And so those are going to have to be equal to each other, right? The force of the spring is going to have to be bigger. That would be F sub spring is going to be equal to Kx. K is 50 newtons per meter. So 11.76 newtons equals 50 newtons per meter times x. X equals answer divided by 50, 0.235. Okay, so 0.235 meters is how far the spring can stretch. Now, I know that it's moving at 5 centimeters per second. So velocity is equal to distance over time. And I'm going to convert everything into centimeters just because it seems easier. So I've got 5 centimeters per second equals 23.5 centimeters. I converted my meters into centimeters over the time. 23.5 divided by 5 gives me 4.7. So I think my time should be equal to 4.7 seconds. And that seems like a reasonable amount of time for the train to pull before the block slips. Cool. Now I'm assuming the train can't slip, right? The train is stuck on its track. If the train could slip, now we're in a whole mess. Maybe it doesn't even have enough energy or enough force to pull the block, but we'll assume that it does. Otherwise, it'd be a terrible question. Okay. A 1 kilogram weight is suspended from a spring, stretching it by 5 centimeters. How much does the spring stretch if the 1 kilogram weight is replaced by a 3 kilogram weight? Okay, so I know that the force is directly proportional to the amount of stretch. In this case, the force is being exerted by the weight, which is represented by the mass. I have tripled my mass, right? So my 1 kilogram went to 3, so that tripled. And since it's directly proportional, I would take my 5 centimeters and I would triple that. 5 times 3 is 15 centimeters. Same spring constant. So I could do all the math, but I also just know it's tripled. I'm good to go. Okay. Other things to remember with the spring constant is that we can use that spring constant for spring potential energy. So if you think back to Unit 4, Chapter 10, when we were doing some energy, the equation for spring potential energy is 1/2 kx squared, taking the amount of distance that the spring is stretched, squaring it, multiplying it by the spring constant and a half, and then that gives you your spring potential energy. All right. Now, there are also some objects that are not really what we would call traditional springs, but they can be elastic. So steel, for example, can be pretty elastic. It can bounce against itself. It can also stretch or compress, but just very, very small amounts. I wouldn't say that it's a spring, but it can be pressed and like compressed and expanded under a great deal of force and pressure. For rigid objects like that, we can figure out their spring constant, K, as equal to the Young's modulus for rigid materials. So Young's modulus for rigid materials is basically like this table, this value of how many newtons it takes per square meter to move it, right? To stretch it. So they're all in 10 to the 10th. That is 10 billion newtons per square meter. Cast iron and steel are pretty high at 20. That'd be 200 billion newtons per meter squared. Silicon, copper, aluminum, wood, Douglas fir is pretty low at 1. Concrete's at 3. So generally, we want to use things that are harder to stretch and break. So like steel is pretty good for big skyscrapers, for their frames, because it's not likely to stretch and break, which is great. For your house, if it's like a single story or 2 stories, Douglas fir is fine for framing it out because there's not as much load on it, right? Much less force on your house than there is on a skyscraper, which is why your framing is probably out of Douglas fir wood and skyscrapers in San Francisco have steel frame. All right. We can represent this showing that L is the length of the thing, A is the area, the cross-sectional area of the rod, and then Y is Young's modulus. Okay. Now I can also find tensile strength. Tensile strength would be the breaking point. How much can it bend or can it be compressed before it actually snaps and breaks? And you can see that we have this kind of graph showing at first objects behave pretty elastically. So like a spring, this is the linear region where it is following Hooke's law. It is directly proportional. Then I get in where I might be deforming the spring just a little bit. This is called the elastic region. So it'll still stretch, but it's not linear anymore. The rod will still come back to its original length. And then finally, I reach a point where I'm going to start breaking stuff. The elastic limit will deform after there. And then eventually you reach a breaking point where the rod will just snap. And then it won't come back together at all. It's broken. Okay, so I can find that tensile strength by finding the maximum force I can exert divided by the area of the cross-section of the rod. Right. So I've got a table here for tensile strengths of rigid materials as well. Polypropylene, glass, cast iron, aluminum, steel. Again, you'll notice that steel has a really high tensile strength. It will not break very easily. You can put a lot of force on it before it starts breaking, which is great. Glass, less so, which we have experience with. Glass breaks more easily than steel does. Okay. All right. Let's do another stop and think. A 10 kilogram mass is hung from a 1 meter long cable, causing the cable to stretch by 2 millimeters. Suppose a 10 kilogram mass is hung from a 2 meter long length of the same cable. By how much does the cable stretch? So the stretch of a cable is like a percentage of growth. And so in this case, it stretches 2 millimeters per meter. Since there's now 2 meters of rope, 2 millimeters per meter is going to give me 4 millimeters total. 2 times 2 is 4. So it's a percentage change, and that percentage would be pushed over the whole length. We can represent this by showing that the force over the area is equal to Young's modulus times that percentage, so the change of L over the original length. This is like the percentage part, or the change of L, the amount of stretch, is equal to the force times the length of the object over Young's modulus for that object times the cross-sectional area. All right, last little piece. Elevator cable stretch. Let's do one. The steel cables that hold elevators stretch only a very small fraction of their length. But in a tall building, this small fractional change can be pretty noticeable. This example uses realistic numbers for such an elevator to make this point. The 2,300 kilogram car of a high-speed elevator in a tall building is supported by 6 1.27 centimeter diameter cables. Young's modulus is 10 times 10 to the 10th. Looks good. When the elevator's on the bottom floor, the cables drive 90 meters up the shaft. Okay, so 90 meters is my length. That is my Y. This is a diameter, so I'm gonna have to turn that diameter into an area. 2,300 kilograms is a mass. The elevator is on the bottom floor and fills up with 20 people, total mass of 1,500 kilograms. There's another mass. The elevator then accelerates upwards. That's an acceleration. Oof, reaches cruising speed. How much do the cables stretch due to the weight of the car alone? Okay, question number one, weight of the car alone. So first, I need to figure out the force being exerted, right? The force is equal to the mass times the acceleration due to gravity, because it's a force of gravity, it's a weight, right? Which is equal to 2,300 kilograms times 9.8 meters per second squared, which is 2,300 times 9.8, 22540 newtons. Now I also have this, and I need an area, because how much do the cables stretch? That would be the change of L, and I know that I have that equation, change of L equals FL over YA. So I've got my force right there. I've got my length, 90 meters. I've got my Y, and now I need my area. So I'm also going to figure out the total area. Area is equal to pi r squared, which is equal to pi times, I was given a diameter, right? 1.27. So I'm going to divide that by 2 and turn it into meters. 1.27 divided by 2 is 0.635, but that's in centimeters, so it's going to be 0.0635 meters squared, which equals times pi, oops, pi, 0.000127. 0.000127 meters squared, but that's one cable, and it says it's held up by 6 of them. So I'm going to also do times 6. So my total area is 0.00 or 0.0076 meters squared. Okay, so now I can plug in all those values. My change of length is equal to 2,540 newtons times the length, 90 meters, over the Young's modulus, which was 10 times 10 to the 10th newtons per meter squared, times the area, which was 0.00076 meters squared. So now it's just a matter of doing the math. When I do all that math, I find out that the change of L in that case equals, it's easier to just turn to the right page of the textbook to pull an answer for that one. 0.027 meters, which is equal to 2.7 centimeters. Cool. So that's like close to an inch. So it just accounts for that inch in the elevator itself, right? When it pulls up to the floor, give it an extra inch. So that is just the stretch without people in it. Then question 2, how much additional stretch occurs when the passengers are in the car? Okay, so the additional stretch of the passengers is going to be due to their mass, and their mass is going to be 1,500 kilograms. So actually, I could just do, because I know that this is a change of the force, right? It's 1,500 instead of the 2,300. So I'm adding another 1,500, but it's asking for how much additional stretch. So if I just do 1,500 over 2,300, and then that's the ratio multiplied by 2.7 centimeters, that'll give me my additional stretch. That's how much difference I've got. So 15 over 23 times 2.7 is an additional 1.76 centimeters of stretch, 1.7 centimeters extra stretch when the people get in. Cool. So that was an easy way of doing that. You could also fully redo all the math. So add in that extra mass in here, and then that changes your force, and then plug in new values, et cetera, et cetera. But this will do the same job. Okay. And then finally, what's the total stretch of the cables while the elevator is accelerating? Okay, so again, this is going to change the force. And in this case, instead of doing 9.8, it would be 9.8 meters per second plus the acceleration of the car, which was 2.3 meters per second squared. So my new force is, I'll use a different color. So my new force is going to be equal to 2,300 kilograms. Total, I'm going to assume with passengers, right? Be more interesting with passengers. Plus 1,500 kilograms, that's my mass, times my acceleration, which is going to be 9.8 meters per second squared plus 2.3 meters per second squared. That changes, so I multiply those out, and that gives me a new force of 46,000 newtons. Then I plug that 46,000 newtons in right there instead of that, and figure my new math. All the other stuff remains the same. Everything else stays the same because it's still the same length of the cable. It's the same material, so the Young's modulus will stay the same. The area stays the same. And then I run all that math again, and I get that the change of L is equal to 0.054 meters or 5.4 centimeters. Cool. So that's kind of like a fun little play around, just changing some stuff. All right. Last piece, as I want to do a real quick Unit 6 and 7 summary. And I recognize that I'm kind of late in this video, and it's a long video, but this is the important part where the AP test is actually going to come into play. So we've done a lot in 6 and 7. It feels like it's bringing together a lot of different stuff, but I wanted to go back and especially focus on angular momentum and angular acceleration and kinetic energy rotational kinetic energy, because this showed up in momentum and energy, but it's also really relevant now for rotational motion. All right, so angular momentum, if you recall, is equal to I times funny looking W, omega, which is the moment of inertia times the rotational velocity. Okay, so L equals IW. This would be equivalent to momentum equals mass times velocity, but it's using the rotational terms instead. Okay. Now, if the net torque is equal to 0, then angular momentum is conserved. The initial momentum is equal to the final momentum. So that would be like if there's no net force for linear momentum. If there's no net torque, then we have conservation of angular momentum. And I can write that equation just the same as I wrote my linear momentum equation for conservation. Identify object 1 and object 2. So here's object 1, here's object 2, object 1, object 2. Figure out their initial and final moments of inertia and angular velocities. Figure out their initial and final moments of inertia and angular velocities, and then set the whole shebang equal to each other. So find all the momentums, add them together in the beginning, add them together in the end, and they should be equal if there's no net torque. All right, another factor is the angular acceleration. So I just wanted to remind you that angular acceleration is equal to the net torque over the moment of inertia. This would be equivalent to A equals F net over M, F equals MA, which is Newton's second law, right? This is Newton's second law for angular acceleration. And then finally, another piece that came up in kinetic energy was rotational kinetic energy. So rotational kinetic energy is 1/2 times the moment of inertia times the angular velocity squared. And then I know that the total kinetic energy for an object is going to be equal to its translational kinetic energy plus its rotational kinetic energy. So the total kinetic energy is translational plus rotational. That means it's going to be equal to 1/2 mv squared would be translational plus 1/2 I funny looking W squared. That's rotational. What that means is if I have an object that is rolling or spinning, and then another object that's just sliding and going straight, the one that's just sliding is going to be going faster because the rolling object is using some of its kinetic energy on rotational, so not all of it is going to translational. If I have two objects that are going at the same speed translationally, but one of them is rolling, then I know that that rolling object has more total kinetic energy because it's got that addition of the rotational part. So this is kind of a hopefully helpful summary, a reminder to go back and check your momentum and your rotational kinetic energy. So you might go back to chapter 10 and chapter 8, where, no, not chapter 8, sorry, chapter 9, where we originally skipped a problem or two if it wasn't familiar. Now might be a good time to go back, remind yourself, oh yeah, those problems are now relevant because now I know what I and funny looking W omega actually mean and how to work with them. All right. With that, we're going to do a few practice problems from chapter 8 and have a wonderful rest of your day.